Voilà, mesdames, messieurs, bonsoir. Bienvenue à cette 4e conférence du Colloque Wright pour la science, dont c'est la 18e édition cette année, comme vous le savez. Merci d'être venus à nouveau si nombreux, si nombreuses, pour ce soir vibrer avec l'oratrice de ce soir. Vous comprenez certainement déjà de quoi je veux parler. Comme chaque année, pour ceux qui viennent cette semaine pour la première fois au Colloque Wright, comme chaque 2 ans, pardon, vous savez qu'on a le privilège ici à l'Université de Genève d'accueillir des orateurs et oratrices scientifiques de grand renom du monde entier. Ce soir ne fera bien sûr pas exception. Et comme vous le savez aussi, cette semaine, il y a une thématique qui a été choisie par le comité de la Fondation Wright. Cette thématique est derrière moi, c'est celle de la gravité. Elle y était, c'est pas grave. La gravité, donc cette force que vous connaissez tous depuis vos cours de physique de base, qui régit notre univers. Et donc ce soir, nous allons aussi découvrir une sorte de matérialisation. Cette soirée, vous le savez, se déroule en 2 parties. D'abord, la conférence elle-même, qui se fera en anglais, avec une traduction simultanée en français. Donc j'espère que vous avez tous, pour ceux qui ne parlent pas anglais, le casque. Ensuite, il y aura une longue session de questions et réponses, durant laquelle vous pourrez poser vos questions de 2 manières. La première, habituelle, avec des micros qui circuleront dans les allées. Il suffira de lever la main pour les demander. Et la seconde, vous le savez maintenant, on expérimente quelque chose, mais qui fonctionne assez bien. On a bien quelques dizaines de questions à travers Twitter. Donc, il y a simplement le hashtag quelque part qui va réapparaître, le dièse, Colloque Wright. Il vous suffit de poser votre question sur Twitter pendant la conférence ou pendant la session de questions-réponses pour qu'elle soit ensuite relayée sur scène par quelqu'un qui m'aidera, en l'occurrence Thierry Courvoisier. Pour cela, je vous demande donc de ne pas éteindre vos téléphones complètement, mais simplement de les mettre sur mode silencieux et de les utiliser vraiment pour essayer de poser vos questions durant la conférence. Voilà, sans plus attendre, je passe maintenant, avant d'entrer dans le vif du sujet de la conférence, la parole justement à Thierry Courvoisier, le président de la Fondation Wright, pour quelques mots d'introduction.
Bonsoir. Au cœur de la science, il y a la mesure. Pour les sciences expérimentales, la mesure est le résultat d'un arrangement physique, chimique ou biologique contrôlé. Et dans ce cas, on peut tweaker, on peut jouer avec les paramètres. En astronomie ou en cosmologie, il n'y a pas d'expérience possible, on observe. En fait, on observe les expériences que la nature a bien voulu mettre en scène pour nous. La théorie, cette semaine la théorie de la gravitation ou la cosmologie, donne un cadre de pensée et permet une description rationnelle du monde. Mais sans un ancrage dans la réalité, ancrage qui se traduit par des mesures, conformes à la description proposée, sans cet ancrage, la théorie n'est qu'un jeu de l'esprit. C'est pourquoi il était indispensable qu'une soirée de ce colloque fût consacrée à la mesure. Et la mesure d'ondes gravitationnelles est le sujet qui s'imposait 3 ans après leur première détection. La relativité générale n'a pas été créée pour expliquer des données, mais bien pour corriger une incohérence entre la gravitation newtonienne et la relativité restreinte. Cela n'a pas empêché que, dès sa conception, les protagonistes aient cherché et trouvé des tests pour confronter les prédictions dérivées des équations d'Einstein à des observations. L'exercice est difficile, car la mécanique newtonienne donne une remarquablement bonne description de la gravitation dans notre environnement. Les effets relativistes sont petits, et petites sont en effet les variations de distance induites par les ondes gravitationnelles sur nos détecteurs. Leur mise en évidence ces dernières années est un exploit gigantesque. La Fondation Wright est très heureuse que Gabriela González ait accepté de nous décrire cet exploit ce soir et de nous permettre ainsi d'asseoir la théorie dans la réalité de la mesure.
Merci Thierry Courvoisier. Comme vous le savez, c'est aussi une tradition. il est demandé chaque soir à quelqu'un, un professeur, un scientifique de l'Université de Genève, de présenter l'orateur de ce soir. Alors, la personne qui va présenter Gabriela González ne partage pas exactement avec elle le même champ de recherche. Ce n'est pas vraiment dans la même direction de recherche que vont leurs travaux. Par contre, il partage certainement, très certainement avec elle, le souci du développement et surtout de mise au point d'extrêmement fins et précis instruments de mesure qui ont permis, en l'occurrence pour Francesco Pepe et ses équipes de l'Observatoire de l'Université de Genève, de découvrir, vous le savez peut-être, il y a maintenant bientôt 25 ans, en 1995, la première exoplanète autour d'une autre étoile que le Soleil. Donc, Francesco partage encore une fois certainement avec Gabriela ce souci de mettre au point des instruments dont nous allons parler ce soir. Francesco Pepe, je vous laisse la parole.
Bonsoir. Imagine for one moment that you have bought a lot of new clothes. You come back home from the store and you panic because there are so many clothes you do not know where to put them. So, okay, fortunately, there is still one small space left in your bedroom. So you say, okay, I have to buy a new cabinet. Okay, so you want to rush to IKEA, but no, first I have to check how much space I have there. So you take your tape measure and you go to the small spaces left and you measure. Okay, it's 105 centimeters. Okay, good. Yeah, but maybe it's 104 or I don't know. Okay, let's take a little bit of margin. Let's say it's 1 meter. So then you are safe, and finally you can go and spend your money in the store and buy this cabinet. Good. We are not here to talk about furniture tonight. Okay, it's about gravitational waves. So what has this to do together? And the link between the two is the measurement. The measurement which is our, let's say as a physicist, our fundamental, the daily bread, how to measure and how to measure as precise as possible. And if you want to measure gravitational waves, to detect them, then you have to do very similar measurements as you did with the cabinet. Okay, you have to measure distances, but not at the same accuracy. So let's imagine you have a tape measure which is as long as from here to the next star. Okay, what is the next star, by the way? Ah, very good. Okay, the next star is the sun. So the second next star, which is the second next star? Please? Proxima, good. So let's imagine you have a tape measure from here to Proxima. More than 3 light years, 4 light years from here, okay? 10,000 billion kilometers. You have this tape, and you want to measure the distance, and you want to measure by how much it changes. And to detect gravitational waves, you have to be very accurate. How accurate do you have to be? 1 centimeter precision will not be enough. How accurate do you have to be? You have to detect changes in distances of the thickness of 1 hair at the distance from here to the next star. Okay, you may think I'm not the best person to do this measurement because of evident reasons. Okay, but I'm the best, no, not the best. I am certainly able to appreciate the difficulty of this measurement, not because only of the hair, but because it's my job. It's extremely challenging, as said Bastieri, extremely challenging measurement. Well, what are these waves? How to detect them? How or what can we learn from them? So that will be explained to us tonight by a leading scientist of the LIGO experiment and the person who was spokesperson at the very moment when this first measurement has been done 3 years ago. So that's Gabriela Gonzalez, which we have the pleasure to welcome tonight. Gabriela was born in Cordoba, Argentina, I think it's the home town of tango, if I'm not wrong. So, where she did also her studies in physics, and where she also got her licenciatura, so the equivalent of the master degree. And one of the first things, I think, results during these studies was to prove that Einstein was wrong. In fact, Einstein said that gravity is not responsible for people falling in love. And I think it's, so I was told this story, and I think very, very nice. So, because it's exactly there where Professor Gonzalez met her husband, and proved that Einstein was wrong. Good. After this, Professor Gabriela Gonzalez moved to Syracuse in the US, where she did her PhD on Brownian motion and gravitational waves. And after the PhD, after also other places she visited on her career, she joined the State University of Louisiana, in Louisiana, where she is at present a professor. She teaches, and she's responsible for the gravitational waves detectors, and also making this instrument more and more precise. So I will finish by saying that when I met Professor Gonzalez a few days ago, I was really impressed by the depth of understanding, technical and scientific understanding, by the clarity of explaining these complex things to me. I'm not an expert of the area, and by her passion. And I'm really glad to invite Gabriela and to talk tonight to all of us to learn about Einstein, black holes, and gravitational waves and other matter. Please, Gabriela.
Thank you. Bonsoir. It's an honor to be here. I thank the Wright Foundation, not just for inviting me to give this talk to you, but for organizing these lectures for 18 years, 36, because it's one every 2 years. And I think this is an amazing event that I hope other cities would do more often. Sharing the science and the passion for science and for culture in general, it's a great thing that we should all enjoy. So let me get into this. You have been hearing about gravity if you have come to the previous lectures of this series. This one is going to be a bit different, but it starts with Newton's law. You all learned about Newton's law in school. You might even remember it. And it's a law of attraction. It explains why the apple fell supposedly on Newton's head, but it also explains why the sun, the earth goes around the sun, why the moon goes around the earth, and it explains all the planetary motions. So it's a universal law of attraction. It's a universal law. It's the first universal law that explains things at very different scales. It explains why we fall, but also how the planets move. By the way, if you don't recognize this or this, you should go and watch this movie in the Bastion every evening. When we talk about attraction, you might think, let's hear the music again. This is actually very nice music, again, in this film. When we talk about universal attraction, sometimes we talk about human attraction and we think about dancing. But there's a lot more than dancing. There's the dances of the stars. Those are the ones that we will be talking about. Now, what we have been talking about is Newton's law, Newton's universal law of gravity. But you know that we are here to talk about Einstein's gravity. Einstein's gravity is different in the sense that it is universal, it is a universal law. It does explain why the sun, why the planets move around the sun, but it doesn't assume that the force, that gravity force, that Newtonian force is instantaneous. Because Einstein, 10 years before publishing the general theory of relativity, had come to the conclusion, and everybody agreed, that the speed of light was a universal speed limit. Nothing should travel faster than the speed of light. And gravity seemed to travel instantaneously. So he came up with this different theory, a relativistic theory of gravity, that says that masses live in a space-time, in a dynamic space-time. When we think about space-time, or at least we physicists think about space-time, we imagine a three-dimensional grid with all the distance, equal distances between the corners, that's space, with clocks all synchronized in every little corner, that's time, and that's how we measure the trajectory of every particle, by defining at what position it is at what time, according to the clock on all those corners. Einstein's gravity assumes the same space-time that we talk about, but it says that every mass, you humans, small balls, big planets, big galaxies, every mass deforms the space-time. And it's easy sometimes to draw the distances. The distances will be different in length near the masses than farther from the masses. Farther from the masses, we'll see the regular grid, but near, it will be different. The clocks will also run at different speeds. So masses change distances and times. And this theory has a lot of different consequences. Let me show you, for example, how it also explains why, if we have two masses, they will see each other, they will feel a force because they see the curved space-time. If we have the sun and the satellite will not go straight, it will go in an elliptical orbit. The Earth will go in a circular orbit because it sees the curvature of space-time. And if the sun disappears, then it takes some time for the Earth to find out. This gravity does not travel instantaneously. It travels at the speed of light. And there are many consequences of this theory. The one I like to think about is the one that tells that if you have two masses, like two black holes, and I like to think they dance the tango, although the music in the movie was different, then the two black holes will move around each other, like Newton said, but they are going to deform space-time. Those are going to be gravitational waves that are going to carry away energy from the systems, and it will make the black holes get closer and closer until they merge in a single black hole. And this happens not just with two black holes, but with two neutron stars. If we have two neutron stars, and we know about neutron stars because we can see radio beams from some of those, then the two neutron stars will be producing these gravitational waves, and they will be getting closer and closer to each other until they merge, probably giving birth to a black hole. And this has been seen. Not the merger, although I'll tell you about that. We might have seen that last year, but this has been seen, this getting closer together has been seen in the 70s by Hulse and Taylor. Joe Taylor was a famous astronomer that looks at radio signals from these pulsars, from these neutron stars, and in the 70s, with his graduate student Roger Hulse, they discovered the first system that was a pair, 2 neutron stars. And they were close, they were so close that they were going around each other with a period of 8 hours. Imagine the Earth goes around the sun every 1 year. And here you have the 2 stars going around each other every 8 hours. So that's very, very close. These stars are moving very fast. They are losing energy to gravitational waves, and they are getting closer together. And that's what they measured. This is a quantity called the cumulative period shift, how much a period changes because the stars, the radius between the radius of the orbit is different. And you can see that the period is getting shorter and shorter. The stars are getting closer and closer together. And that's just exactly as Einstein's theory predicts. In fact, this theory, this prediction, this GR prediction, has a lot to do with calculations that the first speaker of this series, Professor Thibault Damour and Luc Blanchet and others made to calculate how much energy is lost in gravitational waves to the system. This work took many years. Notice that the time in here, the time of the measurements goes from the 70s to the 2000s. These are 30 years of measurements. But before that time, only after 20 years of measurements, they received the Nobel Prize in '93. Now let's do a bit more of the math of these gravitational waves, even though we saw some of this math on Monday. This is Einstein's equation. It looks simple. It says that we are talking about space-time, so we are talking about tensors. If you want to think simply about these tensors, they are 4x4 matrices. So there are these indices that go 0 for time, 1, 2, 3 for the 3 dimensions of space. So this is Einstein's tensor, and it's equal to a number with units. This is Newton's constant, because it's a theory of gravity. This is the speed of light to the 4th power to get the units right. And this is something called the stress energy tensor. So this quantity is calculated from the space-time, from the distances and times. In fact, we calculated with a metric that tells us how different are the distances and how synchronized are the clocks, but we have to take derivatives, several derivatives, and multiply them in different ways to construct this Einstein tensor. So there's a lot of math hiding in here. The stress energy tensor tells us where the masses are, where the energy is, and how the masses are moving. So it has to do with the kinetic energy, with the mass density. All the mass and the motion are hiding in here. So this is what tells us that the mass tells the space-time how to curve, and the curvature of space-time tells the mass how to move. Now, if we want to find gravitational waves in here, we do like we do with Maxwell's equations. We say, well, let's look at the region far from the sources, far from the masses that are moving, and then this is going to be 0 because the masses are far away. What I am looking at, the masses are 0, so this is equal to 0, and this in electromagnetism is a wave equation. In here, this is a very difficult nonlinear equation. But if we assume that the metric is this flat metric that we talked about, this square grid with all synchronized clocks, plus a small perturbation, then what we get is a wave equation for this small perturbation. And the solution to this wave equation is a transverse wave. So if it travels in this direction, it will change distances and times in the transverse directions. It will make a circle, which has all distances the same to the center, convert into an ellipse, and then in an ellipse in the orthogonal direction, there are 2 polarizations of gravitational waves. And if you put the mass back in there to see how the gravitational waves are produced for the mass in there, you can make some more approximations, and then you deduce that the amplitude of the gravitational wave is proportional to the change in time of something like the inertia tensor, which means the non-symmetric part of the system, the non-spherical part of the system. multiplied by these constants that come from the theory, from the initial formula, divided by the distance to the source. And this is a very, very unfortunate formula. Einstein published his theory in 1915. In 1916, he published the first paper, which had several mistakes in there, which he corrected, but not, then he made some other mistakes in 1918. But this formula was already there. And in those papers, he put numbers in here. And he says, these numbers make these effects negligible. These numbers make these effects very, very, very small. If we think about that, those two black holes I was showing in the tango, in the dancing, those were the first system, the first signal that we discovered. These were two black holes with 30 solar mass each, and they were traveling at almost half the speed of light when they merged. They were quite a bit far, but not that far in astronomical terms. They were about 1 billion light years away. And this quantity is 10 to the minus 21. This quantity does not have units. It's a ratio of length divided by length. It tells us how much longer is this distance compared to that distance. That is what Francesco was saying. That 10 to the minus 21 means that if you want to measure that change in the distance from the Earth or the Sun to Proxima Centauri, then you have to make that measurement with the precision of a hair width. Sounds impossible. In math, it's not so much. You can draw things. In fact, you can draw what the gravitational wave would look like before the stars merge. They look like a sine wave that increases in amplitude and frequency. And then the ring down, after they merge, then they dump down. They look like this. In the middle, we didn't know what they looked like. And I remember, because I'm older than I look, it was 20 or even 15 years ago, even 10 years ago, when we seemed to have a race between people using supercomputers to try to simulate this merger, and us building the instruments to measure this, to see who's going to do it first. Are we going to measure? Are you going to simulate it first? Well, it took us a long time to measure these waves. This is the simulation, a simulation that was only first made around 2005. This is a recent one showing the curvature, the space-time curvature near the two black holes as they are getting closer together, producing this gravitational wave. This gravitational wave is a change in distance that would be near the Earth. So it's an oscillation that when the black holes get close, this is 100 milliseconds before merger, then you begin to see large amplitude, larger frequencies. Here the movie slows down, the black holes actually speed up, and at the merger time, then there is a single horizon. It's a mess in here, but here this looks very simple. I have to say that I was actually a bit disappointed because this looked a bit too simple. For us, it looked a bit nicer because that meant that we had simpler things to look for. But we were still building our instruments. The question was how to measure this. In the 70s, Ray Weiss and other people, he was not the only one, but he was the first one that thought about measuring these changes with interferometers and calculated how much noise there could be. An interferometer is a laser beam that's split in two. This is the laser, which is a wave, a light wave. It bounces in mirrors at the ends, and when the two waves come back and get out of the interferometer, if these two distances are the same, then the two waves cancel each other. But if these two distances are changing because there's a gravitational wave going through, then they don't cancel each other anymore. So if we put a photodiode in here and we measure how much light there is in there, then we can tell there's a wave because we will see more light, less light, more light, less light. But of course, we are talking about measuring a part in 10 to the 21. So in the 70s was when Ray Wise and others put numbers to paper and said, well, how sensitive can you make such an interferometer? How quiet can you make the mirrors that are at the end? Well, you would have to suspend, you would have to put them in vacuum. How you would have to make the laser travel in vacuum. You would have to do quite a few things, but how long can you make it? Can you make it long enough so that the distance that you have to measure is measurable? And they convinced, he and at this time Kip Thorne in Caltech were the two that got some experiments going at MIT and Caltech with Ron Driver in Caltech, and they convinced the National Science Foundation in the US in the 90s to build 2 observatories that we call the LIGO observatories. My favorite in Livingston, Louisiana, because it's very near Baton Rouge where I live, and the other one in Hanford, Washington, in the middle of the desert. So one in the forest, one in the desert. Both of these are 4 kilometers long on the side. 4 kilometers of vacuum. You have the laser traveling 4 kilometers and coming back, and you want to measure a part in 10 to the 21 of that. Sounds impossible, but it seemed possible to the scientists that began working on this. In the 90s, I was just starting my PhD. But this was not only happening in the US. It was happening all over the world. Here in Europe, there were 2 European projects, a French-Italian project called Virgo, and a UK-German project called GEO. GEO built a shorter interferometer, 600 meters long. Virgo built a 3-kilometer interferometer in Pisa. And this all happened in the 90s, but these detectors, these observatories, take quite a bit to build. They take about 20 years, 10 years to get it all going, 10 years to make it work. We wanted to measure, like we said, 10 to the minus 21. How small is that? Well, if you multiply that by 3 or 4 kilometers, you get 10 to the minus 18 meters. Let me start this movie again. This is an atom. That's 10 to the minus 12 meters. If you go 1,000 times deeper, you see the proton, the nucleus. That's 10 to the minus 15 meters. Now, if this is 1 part in 1,000 of a proton diameter, and that is what we want to measure. We want to measure parts in 1,000 of a proton diameter over 4 kilometers of distance. People thought it was impossible until it was done. And it was done, actually, in the 2000s. In 2005, we achieved a detector, a noise in the detector that had an amplitude of about 10 to the minus 21. This is the way we describe the noise. When you think about the signal out of the interferometer, we think about the time series. When we think about the noise in the interferometer, we say, well, what frequency? At what frequency you have what amplitude? So this is what that plot shows. It shows how much noise we have at the output of the interferometer as a function of frequency. And this is in strain. That's change in distance divided 4 kilometers. So you see that the noise is large at low frequencies and larger, and it grows at high frequencies. This is our sweet spot, or the bucket, as we call it. This is the place where we have our best sensitivity. And what limits our sensitivity? Well, at low frequencies, it's the ground that moves the mirrors that are hanging in pendulums. So it's the motion, the seismic motion of the mirrors. That was our limit. This is the spectrum that we got in 2010. At high frequencies is the quantum noise in the light. It's the fact that the light, even though we like to think about it as a very nice wave, it's made of photons, and we are counting photons when we are measuring light at the photodetector, and we cannot measure an exact number of photons. There are quantum fluctuations in there. and that is the quantum noise, or if you know some electronics, the shot noise that you measure in your photodetector. So that is what this is. And in the middle, we are limited by the Brownian motion. The mirrors are made of atoms. Those atoms at a finite temperature are vibrating, are moving around. And they're moving around quite a bit, more than 10 to the minus 18 meters. But we are averaging over many, many atoms. So we can measure smaller than that. But we still have a limit. So that's the Brownian motion limit. This is a spectrum that we had in 2010. We had been taking data for a few years at that time. With this noise, we were sensitive to the merger of neutron stars, binary neutron star systems, up to about the Virgo cluster. So that's impressive. Why didn't we see anything then? This was 2010. Well, it's because those pairs of neutron stars are estimated to merge in that radius, in the Virgo cluster, about once every 50 years. So it wasn't so surprising that we didn't see anything, but this had been proposed with a visionary theme. Even in the 80s when it was proposed as a two-phase project. They said, first, we're going to prove that we can build a detector that has a noise of 10 to the minus 21, that can see signals up to the Virgo cluster. And then, by then, there will be better technology, there will be better seismic isolation that will move this limit down, there will be reduced Brownian noise that could put this noise down, there will be reduced quantum noise that will move this noise down, and then we'll be able to see to a 200 megaparsec distance. And on that volume, which is 10 times larger, the rate will be 1,000 times larger, and then we should see several signals per year. That was the bet. Now, look at the time scales. This all started in the 80s. We're talking now 30 years later, and this is what we call advanced LIGO. It was approved in 2008. It began to be installed in the LIGO observatories in 2010. We began commissioning and putting it together in the 2012 or 13. In 2014, we had light going back and forth. In 2015, when the story got very exciting, we had a sensitivity that was not 200 megaparsecs, but was only about 60 or 70 megaparsecs. But let me tell you about the experiment. This is my favorite part, and I'm very sorry I only have a few pictures to show you, but if you ask me, I can talk for hours about this. This is what I showed you is the instrument we use. But I told you that we need this light to travel in vacuum. So these are vacuum systems, ultra-high vacuum, 10 to the minus 9 atmosphere, that move these, that have these beams that are these vacuum tubes that are 1.5 meters in diameter. That's a huge vacuum system. This is one of the largest vacuum systems in the world. Not the largest, unless you count all the detectors together. They have to be protected, not just from the elements, from rain and from wind, but they also have to be protected, and we have to use that. They protect us from fire. There has been 2 fires in Hanford, Washington, that went through the observatory. From hurricanes. There were strong winds going through Louisiana. From cars crashing into it. That happened in Hanford. From alligators getting closed. That happened in Louisiana. From bullets. We had that too. So we are very glad that we had that concrete enclosure. That's all the civil construction. The mirrors themselves are suspended. They are suspended because you might remember, you might have played with this. If you have ever played with a yo-yo, you might remember that if you move the suspension point slowly, then the yo-yo goes along. There's one frequency, the resonance frequency, at which if you move that, if you find that special frequency, then the yo-yo goes like this. That's the resonance frequency. You're amplifying the motion. But if you move the suspension point faster than that, then the yo-yo moves less and less and less. So you're insulating the system. The system, the yo-yo, is moving less than the suspension point at those frequencies. That's why the seismic noise is larger at low frequencies and smaller at high frequencies. Now, we do that. In initial LIGO, we did it with just one pendulum. In advanced LIGO, we have this pendulum, this mass, this mirror hanging from glass fibers, from another mirror, which is hanging from blades, which is hanging from blades. And all of that is hanging from a seismic isolation system, which has layers of metal. And we measure the distance, the relative distance between those layers, and we cancel it. It's an active seismic isolation system. And we put that on top of hydraulic actuators that we use to cancel the earth tides, if we need to. And sometimes we do. So this is a quadruple pendulum hanging from the seismic isolation system. And then you have to put all of that in vacuum chambers. And that's very annoying, because once you put it in, it has to work. And sometimes it doesn't. And if it doesn't, you have to open it and then go into it and then close again. That's why this takes so long and so much time. The laser that we have is a high-power laser. We want to use, we're not yet, but we want to use 10 times more power than we did for initial LIGO. And it's not just a simple Michelson. It's what we call now a dual recycled Fabry-Perot Michelson. That just means a very complicated interferometer. This is a beam splitter. These are the mirrors at the end of the 4 kilometers, but we put some mirrors in between to make the light go back and forth a few hundred times. That increases our sensitivity. We actually make, as I said before, the light coming out of the interferometer has destructive interference. So most of the light is going back to the laser. We don't let it go to waste. We put another mirror in here to make the light go back and forth. We call that power recycling. And we put another mirror at the output that we called signal recycling mirror. So this is a very complicated optical topology, which means a very, very complicated engineering system. Because to make this work, you need to have these mirrors at such the right distance so that when the light goes back and forth, it goes back and forth on itself. It has constructive interference. And that only happens if you put the mirrors and some integer number of wavelengths between them. So we need to push on the mirrors all the time. We have thousands of feedback control loops to make this work. So it was 2015. We were at a sensitivity of about 60 megaparsecs, like I mentioned, 80 on good days at Hanford. That's not what we wanted to be. We wanted to be at 200 megaparsecs. But we had already made plans with Virgo, because by this time we were all working together. Virgo was going through a very similar process also with initial Virgo detector generation. We took data. They had similar sensitivity. They had advanced Virgo funded. And that was going on. It was funded a year later, so it was a year behind. But we were working together, looking at the data all together. So it was 2015, and we had already planned years before that by 2015, we wanted to take data for a few months. We probably wouldn't see anything, but we wanted to practice how to take data, how to analyze data, and then we would go down and keep improving the detector until we got 200 megaparsecs. But as you probably all know, on September 14, 2015, nature surprised us. We were getting prepared to take data 24/7. At that time, we were in what we called an engineering run, taking data once when we could, but still doing a lot of testing and diagnostics. And we saw this, which I know doesn't mean much to you, or perhaps doesn't mean as much to you as to me, but I am wearing this. So you can tell how much it means to me. It still makes me cry. It's a time series, 2 time series, one on top of the other. In blue It's a time series in LIGO Livingston. So this is a signal from the photodetector with some minimal filtering we've done in there. So this is a photodetector, which in general, it's a noisy time series. But then you can see that this is a sine wave that grows in amplitude and frequency and goes down. That's just like what people had predicted black holes would produce. But of course, the detector produces a lot of noise. So how do we know this is anything worth looking at? And that's because in Hanford, we saw on the photodetector at 3,000 kilometers of distance, the same signal only if we shifted 7 milliseconds. So here there were two signals in two photodetectors 3,000 kilometers away that look like gravitational waves of large amplitude. Look at this, 10 to the minus 21. But on a very short time scale. This is only 1/10 of a second. So this would have been produced by big black holes. We could not believe this. It took us months to convince ourselves that this was noise. And we had to do a lot of sophisticated analysis. We didn't look at this by eye and say, oh, yeah, that looks like a gravitational wave. We actually had to do a lot more work than that. But we had some fun, too. We, for example, made noise or music, if you want, with it. Let me show you. It's difficult to hear it in the beginning, so we added 400 hertz. That's a natural noise. It's very difficult to hear it, but let me play it again. As you can tell, we not only wear it, we dance to this. This is a time frequency diagram, and I will show you that again. This was our discovery. Now, there were a few date coincidences that I couldn't stop by talking to you about it. One is actually a date coincidence on that September 14, 2015. This could not have been done on purpose, but as you probably know, Einstein's theory of relativity was developed by Einstein here in Switzerland, in Bern, and his apartment has been made a museum, Einstein House, and that house has been named jointly by the American Physical Society and the European Physical Society as a historic site, and that dedication happened on September 14, 2015. As people were putting this plug in there, a gravitational wave was going through Earth. It's amazing. On February 11, 2016, it took us a few months, like I mentioned, to be sure, to send the paper for publication, to get referee reports. We could say we did it. And we had this press conference in Washington, D.C., and you could see Ray Weiss and Kip Thorne in there. Franz Cordova, the director of the National Science Foundation, she was presiding the press conference. I was there because I was the spokesperson of the LIGO Scientific Collaboration. Dave Wright was and is still the executive director of the LIGO Laboratory. And I learned, actually this morning, that this is our own Olivier MC in here. He was there on February 11, too. It was a press conference, so there were a lot of journalists. Now, the date coincidence I was telling you is that February 11, 2016 was the first time that was celebrated as the International Day of Women and Girls in Science, and it was declared so by the United Nations, by the UNESCO. And it was such a nice coincidence, not only because of the date, but just by chance, among the 5 scientists that were there were 2 women and 1 presiding the press conference. So we thought it was a great way to start celebrating. Of course, we celebrate every September 14, not necessarily February 11. You probably heard that this earned the Nobel Prize in Physics in 2017 to Ray Weiss, Kip Thorne, and Barry Barish. He was an executive director of the LIGO Laboratory for 10 years, managing it to get to the to get to the sensitivity that we wanted, but it was nice to know or notice that in the press release of the Swedish Academy, the affiliations are not Caltech and MIT, they are LIGO-Virgo collaboration, because this was really teamwork, and that was recognized as such. Who is that collaboration? Well, it's a lot of institutions. Just LIGO has 100 different institutions in 20 different countries. And when you want to think about these people, who are these people? Then you probably think about Einstein. He wasn't in the collaboration, but that's the kind of physicist that you probably imagine in the collaboration. Joe Weber, he was the first one in the 60s who started thinking about measuring gravitational waves. Again, he died. He was not in the collaboration, but he's the kind of physicist that worked in this. Ray Weiss, Kip Thorne, these are my two mentors, Peter Solz and Ray Weiss. But it's actually a lot more diverse than that. This was just a fraction of the people that were in that February 11 conference. These are the groups in Livingston and Hanford and MIT and Caltech. But even there, you can see lots of colors. So not everybody has gray hair. Not everybody is above 50. We do have young people, but those are the majority. When you look at each group in particular, my group on February 11 looked like this. These were the people. These are the physicists you need to imagine. When you think of physicists, when you think of scientists, these are the images you should be thinking about. OK, let me go back to science. Those were the other matters in my title. I told you about this September 14 gravitational wave. We took data for a month. When we made the announcement, we had analyzed this month of data. We had a hint of another signal in there, but nothing very clear. In December of 2015, we saw another signal, smaller, so we cannot see the very nice time series I showed you. You can only see it if you do the sophisticated analysis that we do. This was we deduced formed by two smaller black holes at about the same distance, but smaller black holes, and why the signal, that's why the signal was smaller, although a bit longer in our data stream. So now we had 2 or 2.5, depending on how you count. We went down in 2016 to improve the sensitivity in our detectors. We had in one of the LIGO detectors, we reached 100 megaparsecs, so that was a good, nice thing. Virgo was still not ready to operate, but we were waiting for it to come online, so we started taking data in late November 2016. January 4th, we saw our third black hole. June 8th, we saw another black hole, and at this rate, we were kind of tired of black holes because it took a lot of time to discuss and do the calculations, and they all kind of looked the same. But we were waiting for Virgo to join. Virgo joined on August 1st. We needed to go down. LIGO detectors needed to go down on August 25th, so we were tight, but we said, it's going to be nice to take data for at least a few weeks together. And on August 14, we saw another black hole merger, but this time with 3 detectors. And that's very important, because with 3 detectors, you can triangulate. And if you triangulate, you can tell all our astronomy friends that have telescopes around the world and satellites in space, look there. Before, with all of these other detections, we had been telling astronomers, well, these are black holes, but please go and look there. And they did, but when they said, well, we didn't see anything, we said, well, it was black holes, it was such a big area, I'm sure you didn't cover everything, so we cannot conclude much. But with this black hole on August 14, the area to look for was a lot smaller. They still didn't find anything, but this became a lot more exciting. By then, we were happy. We were ready to finish, but we still had a few more days to take data. But by then, we felt ourselves astronomers because we were doing at least black hole astronomy. These are the masses of the black hole systems we had discovered by then. 5.5 systems, 5 and this candidate there. This is what we knew about black holes before from X-ray astronomy. You can't see black holes, but if the black hole is near another star, then that other star will be moving around the black hole, and that star will be emitting light. And the matter falling into the black hole will be falling very fast, and it will be emitting X-rays. So the black hole doesn't emit anything, but if there is stuff nearby, you can see that stuff. And those are the X-ray black holes. And those have smaller masses than our black holes. We don't know why yet. Astronomers are looking into this, whether these are different populations, but that's a nice thing. Now we have questions, we have observations, we have science to do. Now that was August 14. August 17 was the big surprise. On August 17, we saw another gravitational wave, but this one was a lot longer, which meant that the masses were a lot smaller. And not only that, but they were very close in time, less than 2 seconds, from gamma rays that were detected by the Fermi satellite and by the integral satellite that were just surveying. They didn't have to go and look there. They were surveying, and they saw these relatively weak gamma rays, but very close in time. By the way, the data center for the integral and other space missions is here in Geneva. So you should all be very proud of this data. So this was amazing, because this meant that if these masses were so small, then they were probably not black holes. They were neutron stars. And if they were neutron stars, then they would produce electromagnetic waves. In fact, mergers of neutron stars had been thought to be the origin of short gamma ray bursts. And these are short gamma ray bursts. They are small, but we thought, well, maybe that's because we are seeing them off axis. We are not just seeing the collimated gamma ray. Of course, what's the first thing we did? Well, it wasn't quite the first, but it's the first thing I show after this. It's sound. Let me show you what this sounds like now. It's a long gravitational wave. It has more than 100 seconds. But now, there's a ping. We have 2 instruments in the orchestra. Now it's not just gravitational waves. But now, because we had 3 detectors, then we could point and we could tell people, go and look there. And they did. And in that region, which was our localization, there were quite a few galaxies. And because we had a distance, and they said, well, we are going to concentrate in these galaxies that are at about the same distance. And in one of those galaxies, they saw a bright spot that night. And that bright spot became dimmer and redder. And then from the same spot in that galaxy, NGC 4993, there was light from the ultraviolet and the infrared, and the radio waves came 10 days later. So these were all clues that this had been a neutron star merger, and now we had a lot of information to put together a movie. This is a NASA movie, so it's like a Hollywood in science. We do a lot of nice visualizations. These are the 2 neutron stars producing gravitational waves. And then the gamma ray burst that we see at an angle, and then this isotropic burst, electromagnetic waves, and this is a shock wave that produces a wave on the X-rays. This has been one of the most observed events in astronomy now. It's amazing. We had to go down, so we've been down since then, but the next few years, we are now down in here, working on our detectors. We're probably going to begin taking data again with at least 100 megaparsecs in both LIGO detectors, 60 megaparsecs in Virgo. We are going to begin taking data, all 3 detectors together. In February next year, we'll be taking data for a year. We will still not be where we want to be, so we will go down again. We will begin taking data again. Kagra, the Japanese detector, will join us, so we will have a network of detectors. This is just the beginning. We are at the time when probably a few months later, when Galileo pointed his telescope and began looking not just at the moon, but at our moon, but other moons, discovering the motion of the planets and the motion of moons around other planets, that is what we are doing here. And this is not the only way to see gravitational waves. Gravitational waves, depending on the source, come in different wavelengths with different notes for the music. And for that, you need different instruments. So for gravitational waves produced by massive black holes, you want a much longer detector. That's a space detector. For gravitational waves produced by supermassive black holes, then you want an even longer detector, a galactic detector. You can do that if you measure the radio signals from pulsars in our galaxy. If you want to look at the early universe, that's more difficult, but scientists are still trying to do that by looking at the polarization of the cosmic microwave background. Now, LISA, I think it's every gravitational wave scientist's favorite project. It has been in the books since the 70s. It was thought about at the same time that LIGO was in the 70s, but because it's a lot more expensive, it has taken its time in being approved. It was only approved by the European Space Agency a couple of years ago. It's a project with 3 satellites that would be 1 million kilometers away from each other, going around with a system going around the sun, 20 degrees behind the Earth. And the spectrum, the noise spectrum, would be not that different than LIGO spectrum, going higher low frequencies, going higher high frequencies, but the sweet spot is at about 10 to the minus 2. That's 10 millihertz. So that's a much lower frequency. We will be able to see these massive black holes at the center of the galaxies, the merger of galaxies. We will be able to see small black holes or small stars falling into the black holes, white dwarfs in our galaxy. This will be so much data with such a high amplitude that we are all waiting for that 2034 launch date. We have all learned to be patient. But we know it can be done because in 2015, a test mission was launched, and the results came last year that were amazing. This was a mission that had the same freely floating cubes that would be in the LISA satellites, except that instead of being 1 million kilometers away, they were only 10 centimeters away, well, a bit more than that, but it was about this distance, but with the same technology to measure the distance and to move the satellites, and it had the sensitivity needed to be. That, we called it the quietest place in the universe, in space. We don't say universe, but I don't know what's that. But that's not the end. This is just the beginning of gravitational wave astronomy. So keep posted, because there will be a lot more news coming, and not just in the next few years, in the many decades to come. Thank you.
Well, thank you very much, Gabriela, for this really fascinating presentation. It's now time for a question. As a reminder, you will be able to ask your question both in French and English. Again, both live here with microphones and on Twitter. The hashtag should be somewhere, so it's the hashtag Colloque Wright. Please do ask your question on Twitter as well, and they will be relayed on stage. As you know, we have the chance to have tonight 2 other guests for this Colloque Wright. And I'll have the great pleasure now to invite on stage Claudia de Ram, who was here yesterday, and Andrew Strominger from the University of Harvard. So maybe I'll start with you two, our 2 guests. with a simple question, where were you and what were you doing and what did you think when you learned that Einstein's predictions were finally discovered?
Well, I guess the first thing I'd like to say is thank you for the very beautiful talk, Gabriella. But
Is that your
I'd
mic?
like to say as somebody who's completely out of the field. Microphone.
Excuse me.
Is it on?
No, what?
Is it? Try again.
Is it on?
Can maybe someone bring us a microphone? One of the two.
Do you have
Try
one?
again.
Oh, no, that.
There's a light on now.
Try again, Andrew.
Hello? Okay.
So again, the question.
Well, I'd like to say thank you for the beautiful talk, Gabriella. I enjoyed it very much. It had one very serious shortcoming, which is that it was overly modest. And I think she had to be because she was part of the collaboration. But it's not an understatement to say, and I can say this because I had absolutely nothing to do with it. It is the most interesting thing that has happened in observational astronomy since the discovery of the telescope, which was quite some time ago. And it's as if we could, before their work, we could see the universe, and now we can hear it. And there really seems to be no end of the new things that we might be able to discover. It really is an incredible moment in the history of science. And as for my personal reaction, when I saw those symbols, I cried. I mean, I have spent my whole life thinking about black holes. They're an abstract, theoretical object that was discovered by Einstein and Schwarzschild a century ago, but we've never gotten to see them in any way that we could infer them in some indirect way, but to actually see a signal that came out from them, we hadn't been able to do that. And LIGO had been going on for 50 years. Gabriella, I know because I talked to her about 6 months before they saw the signal, was very optimistic they were going to see something. But they might have gone on for another 50 years with bad luck and machines that didn't work. And there was no guarantee that they were going to cash in the way they did. But to suddenly have these black holes, which are clearly the most weird and mysterious and fascinating objects in the universe, to come into full view in fabulous detail, those signals that matched like that, was just kind of an overwhelming, for me, was a personally, because I've spent my life trying to understand them, for me was just a personally overwhelming experience. And I'm just very grateful to, not just at a scientific level, but at a personal level, very grateful to Gabriella.
And Claudia?
Well, thank you as well. Beautiful talk, and also thank you to the LIGO collaboration. It's also something I didn't expect to happen. It's really changing, as I mentioned yesterday, the way we do science at the moment. It has already changed my career, changed the way I'm thinking about the universe. It really changes everything, and it's something I was hoping for it to happen, but somehow I didn't expect it would actually be so beautiful and match so well. And as Andrew said, it's the whole collaboration from LIGO, but also the whole team that was able to simulate the signal with such a good accuracy, and this precise match between the template and the observation is absolutely amazing. And something I like to note maybe, because this was one of the highlights after the announcement, that it proves that Einstein was right, and that was emphasized as if the main thing about the detection was to prove that Einstein was right. Funnily enough, it probably doesn't prove that Einstein was right, because there was a little bit of a back and forth between whether he believed gravitational waves did exist or not, whether they were just a gauge artifact or not. And but really, the point of detecting gravitational waves is not about saying whether Einstein is right or wrong, and it's really about doing science, and we can do science now. It's really the opening of a new era. It's not about finishing a chapter and saying, okay, Einstein was right, now we can move on. It's really opening up. We're really going to do a whole new set of science thanks to that, and it's really incredible. It's really incredible for me as starting new science in that direction.
So let's ask you the question. How did you feel when you actually showed Einstein was right? How do one feel to show Einstein is right?
Well, like Claudia says, it wasn't, I don't think I know anybody who doubted Einstein was right. We were counting on him being right. We just wanted to measure these signals to begin looking or hearing the universe, doing astronomy in a different way. But in the beginning, we all felt incredulous. We thought this was a joke. We thought that somebody had simulated these signals and put them in the data without telling me, without telling us.
No, but you're joking, but that's, but that's exactly what you did in 2010. You didn't mention that in your talk, but in 2010, you just injected false signals to check how the team would react and if they would be able to detect actually the waves. Is that correct?
We did that several times, as I mentioned, with the initial LIGO detectors that we took data between 2005 and 2010. We had several science runs, we call them. Having a visionary vision, we said we will call these observing runs. But in those science runs, because we didn't have enough sensitivity, we didn't think we were going to make detections. So when we analyzed the data, we had this prejudice that anything we saw was probably not the gravitational waves. And we had developed sophisticated methods of vetoing anything that looked like any detection. And we were very afraid that we were being biased against detections. So we said, well, we know how to simulate signals. We are going to designate a team. We called it the injection team. We only had 4 or 5 people, and they are going to decide what kind of simulation they are going to inject in the data, whether they'll inject, when they will inject the data, and they did that several times. There's actually books about these things by a sociologist, Harry Collins. And we learned a lot from those. In fact, the first time this was done in 2000, I think that was 2007, we missed an injection quite as strong as this one we simulated here. And we missed it because we were too conservative in vetoing things. And then in 2010, we had another one that we saw, but then we realized that we didn't have all the tools ready to estimate the parameters of the signal. So we had to develop, to run around to improve those methods. So we were ready to do those simulations. We were planning to do these blind injections, as we call them. And part of the testing we were doing the week before the discovery was testing these simulations. That's why when it happened, everybody thought I had authorized this, and they asked me, so did you authorize? You were not supposed to do this until we started. And I said, no, I didn't, but nobody believed me.
So you mentioned being incredulous. At this press conference, I went to Kip Thorne, and Kip Thorne is a really surprising and funny person. He helped, for example, put the movie Interstellar with the design of the black hole. And I asked him, are you excited? And he said, well, he didn't answer, but he didn't say no, but, well, no, he said, I'm satisfied and relieved. Because with rhinovites, they spent decades to go to the NSF to ask for millions, if not billions. So he didn't show excitement, but just relief. So did you feel that way too?
I felt that on February 11. Yes. During the months it took us, this happened so much at the beginning of our, like I said, we hadn't begun taking data, so we had not characterized the noise of the detector. We thought maybe the detector has a new noise source. We have lots of transients that we don't know where they come from. We know are not astrophysicals because they don't happen in the detectors at the same time. But maybe this new detector has transients that look like gravitational waves once an hour, and we haven't taken enough data to look at that. So we decided that we had to take data for at least a month to be able to have 15 days of coincidence. And if in the analysis we didn't see coincidences that look like those, then this would be a good candidate. But we didn't know that until we took a month of data and we analyzed that month of data, which took another couple of weeks. So it was building stress. It was excitement, but I have to say it was so stressful.
But the idea here is also to say that, I mean, all the money invested in the project was, in a way, justified. Andrew and Claudia, do you also feel indebted to society for all the, I mean, the public money you get for your research, and how do you then show it, maybe?
You know,
please take my, yep.
Actually, on the contrary, the LIGO budget is incredibly small. It was a cheap experiment compared to what they discovered. It was around 800 million. And that could be compared to many other things which were orders of magnitude more expensive and discovered much less. So in fact, the funding situation, the funding agencies, I don't think have done an especially good job of being sensitive to what is and what isn't good science. And the resistance that they put up and the amount of time that Ray Weiss had to spend running around talking to people, raising money, when he could have been working on the science is not heartening.
Simple question, why? Why is that so? Well, maybe especially in the US, but
no,
I presume it's the same.
I'm not an administrator, I'm not a politician, but this was clearly great science. I think people in the field understood that it was great science, but they didn't, for some reason. I guess it's because there's no history of it. It's a new field. And there aren't elders in the field running around. Well, now there are. Now there are 2 or 3. But there aren't elders of the field running around with Nobel Prizes that can talk senators into getting more money out of Congress. So it was a very, very meagerly funded project. And they should have funded it, I think, and I've said this in public, they should have funded it at 5 or 10 times the level. We'd have had these results 10 years ago, and we'd be way ahead.
Claudia, I mean, same question. Do you feel sometimes, indebted for the public money you get for your research?
Well,
indebted to society.
I think funding is very much a bias subject, but I'm definitely indebted to society for appreciating what we're doing and for being on this, all of us together. I don't think I can really comment too much on the funding aspect of it. But seeing a room like tonight, full of people excited about listening, about hearing, about understanding what the subtleties are, of course, I'm very indebted, and thank you for being here.
Gabriella, I have to ask you this question before going to the room. Last weekend, there was an article in the New Scientist by Danish scientists saying that your work, not your work, I mean the LIGO's collaboration's work was fake, and that actually the grav waves were fake. Can you tell us more about this and what it is about, and why did they come to this conclusion 2 years after, etc.?
Yes, something that we had decided even before the discovery is that with every detection, we were going to not just publish a paper, but make public the data around that, an hour of data, not just the fraction of a second, but about an hour of data from the detectors, for people to be able to reproduce what we did. Of course, the analysis, the statistical analysis that we do to reproduce how often this can happen by chance could not be reproduced until we made public the whole data, but we have done that now. Again, with the intention that people can reproduce these results. I have to say that, again, it has a bit to do with funding. It's a lot of work to release data because you have to make sure that it's well documented, that it's calibrated. You have to do all the visualization. So we have people dedicated to do that who could be doing science, but we decided this was very important because we wanted people to see what we saw. There were only a couple of groups, including them the Danish group led by Andrew Jackson, that said, well, in this figure that you published, if you subtract the simulation from that beautiful waveform and show, the one I'm wearing, you have a residual that still looks correlated in your two detectors, so it looks like you have correlated noise. And we said, no, that's not true. Well, that's not how we do the analysis. We do the analysis in a statistical fashion, but unless you have the perfect waveform, you will have correlated residuals, but then we have these other detections, and this discussion has gone back and forth a lot of times. At this time, it's they do the analysis in a way which is not the way we do the analysis to do detections. It is possible that using methods like what they use, you could get different ways of estimating parameters, meaning that looking for the weight of something to subtract that leaves nothing correlated, but then you would be too sensitive to the noise, so we don't think it's the best way. It might be a good way, but we are living for the scientific community to decide.
And maybe the best explanation is that you saw other gravitational...
We have seen, again, doing all this. We do two different analyses. One is doing the statistical analysis to see whether this could have happened by chance, this coincidence could have happened by chance or not. And then we do another analysis with templates to see, well, how do we match templates to learn the masses and the distance and the localization. And obviously we got some things right because the localization of the neutron-star merger was right on target. But we think that's the best way of doing those. There might be other ways. Again, we leave the scientific community to do these things. We are preparing a tutorial that explains, perhaps better than we have done in previous papers, on how we do the analysis, so and trying to publish the codes, the actual codes, which most of them are out there, but they're not easy to follow. I'm afraid we don't spend enough time in documenting the codes. But we try our best for people to reproduce the results because we believe in those.
Yeah. So it's time now to open the room for questions. Are there some questions in the room? Yes, one at the very back for once. Can you raise your hand, please? Can you raise your hand higher, please? Yeah, thank you. Is someone coming to you?
Good evening. Thank you so much for your introduction. I have a financial question about all of this, and it is a question for the room. As a lot of you might already know, science is very costly. We heard tonight, Gabriella said that those experiments are actually very expensive. I was wondering, a lot of money has been, sorry for saying that like this, wasted in the scientific endeavors of astronomy. How do you think this kind of work could justify further investigation in your field? And especially about the interesting aspect of your presentation about the idea that maybe some of the quantum fluctuations of the vacuum could be actually used to detect some gravitational waves. I hope some of you in the panel could answer that. Thank you.
Thank you. May I add something? I mean, you said many times it opens a new era, right? So what's to see out of that window?
Well, of course, with this kind of instruments and with most of astronomical instruments, we are not developing things that can be used to cure cancer or diabetes. I have diabetes. I would love for my experiment to help, to help with that. It doesn't. It doesn't directly. But the technology that is developed and the brains, the human resources, the people that work in these experiments and then go off to the rest of the industry. I have students that are working, and we have in LIGO students that are now working in a lot of different industries, and they had the best education on how to do good things, how to discover, diagnose things, how to discover noises and reduce them. That's the immediate payoff of these basic experiments. But there's a long-term payoff that it's very difficult to predict. There are many people, especially in developing countries like Argentina, where there's a lot of discussion on, well, if you are going to spend money in science, maybe you should spend it in what you know it's going to be applied right away. Well, if that had been done 100 years ago, we wouldn't have the laser today. We wouldn't have a lot of technology that we use today that was very basic science when it was developed. So there is a very selfish interest in spending money on basic science, science that for now, it's for understanding the universe better.
So that's about the applications, but what are the, what windows does it open in your field of research, and maybe yours as well, in terms of new exploration, new quests?
Of course. I mean, that is what happened with Galileo and the telescope, right? It was just two pieces of glasses and a cylinder, but putting them in a certain way.
What kind of questions do you ask yourself now that you have the waves? With
us, look, it's only been 3 years since the discovery, and just with the first discovery and then the ones that follow of black holes, we have big questions. How do black holes form? We always thought that black holes started small in supernova explosions or in the merger of neutron stars, but now we can see that they get up to 30, 60 solar masses and not at the center of galaxies, not all in the same place. So astronomers are very intrigued about this. There are competing theories. That's black hole astronomy. That's a whole new window that now we have a way to measure. With the discovery of the merger of neutron stars, that is very strong evidence not only for that neutron stars merge, we always kind of suspected that, but that they merge and that there is a big explosion, and that is what's supposed to be, that's the current theory on how gold is produced in the universe. That was a mystery.
Do one of you want to add something shortly?
I mean, as I mentioned yesterday already, just from the few detection, I mean that in a good way, of gravitational waves, we already have much better understanding of what dark energy is not, and so we can really focus on the important things. From the the first direct detection of gravitational waves, the LIGO-Virgo collaboration was able to put a bound on one of the parameters of gravity, the graviton, on the mass of the graviton, which is already better than what we know for light. From the one direct detection of gravitational waves, we already understand some parameters of gravity better than we understand light through all the detection. Everything we have seen so far was through light, and yet that for thousands of years, and yet the one direct detection was already able to give us some understanding of gravity was well beyond what we knew for these thousands of years of detections of light. It's incredible. We can't right now tell you everything that we're going to be able to do with gravitational waves because it's really just the opening. But there's already been so much science being done. For me, it's a real beginning.
Andrew?
Yeah, so I'd like to answer your question in a more general way. And I took your question to be, why do we spend so much money on science? And I think there are really two different answers to that question. One is a practical one. So right now, about a quarter of our economy is directly tied to quantum mechanics. So quantum mechanics, the value to us of quantum mechanics is many trillions of dollars a year. The cost of developing quantum mechanics 100 years ago was well under $1 million. And investment by society in basic curiosity-driven research has been, in the long run, by far, the most lucrative investment. If you had asked Max Planck or Niels Bohr or Schrödinger or Heisenberg, what applications do you see of quantum mechanics? I don't know whether they would have been willing to answer or not, but had they answered, their answers would have been ludicrous. They couldn't possibly have foreseen the way that their basic curiosity-driven research would transform the world. So we shouldn't only be working on things that we see lead to a patent and a startup in 5-year time. We should be trying to understand everything that we understand, even those things that may have a 100-year time scale to have technological, financial benefits. But having said that, that's not the reason I do what I do. I don't work on basic problems of black holes so that my great-great-grandchildren will be able to live a more financially comfortable life. I work on these problems because I think it's part of being human, and one of the unique things about being human, to have this urge to understand at the most basic level the world around us. And I think that that is satisfying for all of us, and witness the number of people in our room. I don't think there's anybody who's in here because they're looking for a hot tip on what stock to invest in order to in order to cash in on the advances that have come from gravity waves. It's because we're human and we're curious about that world, and that curiosity is a good thing, and we should feed that. And I think the amount that is invested in basic curiosity-driven research is tiny. It's less than 1% of the money invested in science and in technology. It's just tiny. And these people were all working on practically, the graduate students especially, I assure you, were working on starvation salaries because they wanted to know about the world. And anyway, that's my view.
Well, thank you very much, Andrew. So let's go now to Twitter for a few questions.
You have answered actually already 2 questions that were asked on Twitter, but there's a third one, which says actually you have now a certain frequency of events. you know the sensitivity of your instrument, you know how long it was being run. So can you deduce out of that the density and the frequency of these events in the universe? And out of that, can you then deduce something about the density of black holes?
Yes. And I have to say that although we were not sure we could do that, but we did it even with just one detection. In the paper that we published, with the first detection, we said, well, the rate of merger of black holes in the universe is not 0. And we didn't know that before that one discovery. But we put a range, and now we know that rate quite a bit better. However, with the sensitivity we have, we are still looking, even for black holes, we're looking at the very near universe. That's why we really want and need more sensitivity to look at a bit farther to make sure that this rate is not distance dependent, which means time dependent, because the farther you look, the farther in the past you're looking. Of course, for neutron stars, we just have one. So we still we don't dare to calculate the rate from just that one, because we do have an estimate for the rate of merger of neutron stars from the knowledge that we have from binary pulsars in the galaxy. So we can extrapolate, and we are counting on that. But that's, again, another reason why we want to have better sensitivity to make sure that we see many mergers of neutron stars. What I really want to find out is what's the what's the rate of unexpected signals.
So there's one question here in the front, please. And I'll take then the very last one because time is running. Le monsieur, ici, here, ici, devant. Time is running fast.
Yes, the woman behind Jorge also.
Thank you for your brilliant talk, and I just want to comment on the previous one. First, we need science, and I love the way you spend money. Thank you. But my technical question is, the kind of devices such as LIGO, is it simply the best way to detect gravitational waves, or it's just the only way today?
Well, if you really, it depends on how you measure what's best. If you really want to look at gravitational waves that have the largest signal-to-noise ratio, then LISA is the best instrument. And that's why we have all been trying to get LISA funded and supported for decades now, and we are so happy it's going to fly. In LISA, we will have signals from mergers of black holes that will have signal-to-noise ratio of thousands. Our best one had a signal-to-noise ratio of 25. So that's the best way. But you're only looking at certain sources. With our detectors, you can look at mergers of neutron stars and small black holes. With LISA, you can look at million solar mass black hole mergers and white dwarfs. We cannot see white dwarfs. So depending on the signal of the source you're looking at, then you need different instruments.
So very quickly, one question here, one here, and then if we have time, to the back.
So with the LIGO-Virgo collaboration and the teams before the first detection working on finding something, refining methods and so on, not having a detection. And now we have a detection, we have several detections, the Nobel Prize. So how has the work, or has the work changed in the teams, in the different institutions in the LIGO-Virgo collaboration?
I think so. It hasn't changed what we do. We're still working. Every person of these $1,000 teams is a 1,000-people team is working on small things that need to be that need to be solved. So everybody's working on a small problem, on getting the calibration more precise, or making the laser less glitchy, or it's not working on the big thing. But, of course, now, with everything we do, we can say, now we can see black holes a bit farther. So we do it with more enthusiasm. But it's about the same that we were doing before.
Madame?
Hi, I'm going to try to turn this into a comment versus a long question. So my comment is not as challenging. I'm more of a fan of yours. I've been a fan for years of your studies, watching your videos, all of you. And I'm not a scientist, I'm a dancer. I'm a choreographer. I actually created a show in San Francisco, I'm based there, called Quantum Dance, working with a CERN scientist. And now I'm creating one called Gravitational Dance. So I just wanted to say that I do believe that it's worth putting money in science, absolutely. I think that today we are all suffering from many things, and I think that one of the problems is that people are too concentrated on their own small quotidian problems of every day instead of looking on the outer of themselves and understanding astronomy better, understanding the universe better is such a beautiful way to think outside the box, think outside borders, outside limits, outside the limits of your own skin, and just understand the humanity in a better way and how we're all connected through particles, all dancing, all vibrating together in waves. I think it's beautiful. And my quick question is, I used to separate particle physics and astrophysics, astronomy. That's why I created 2 shows, because I wanted to show the beauty of the small and the beauty of the big. But now with gravitational wave studies, I'm a little bit confused. I feel like it's actually a beautiful symbol of how the 2 worlds are coming together, because I'm noticing how scientists who are more concentrated on particle physics are working with astronomers, with astrophysicists together on this. So is this something you would agree with, that is actually something that's creating peace between these 2 worlds, and people who are fighting to get funding, shouldn't they all work together?
And can I go further and asking if it's maybe one way to merge, to finally merge quantum physics and gravitational physics from Einstein? Yeah, you leave that to Andrew.
But about the small and the big, I have to say that is what personally attracted me to this field. It's thinking that you have to make these instruments that were big by human standards, 4 kilometers long, but you had to make them so precise to measure these minute distances to learn things that happen, that were produced by big things very, very far away. That connection between a big instrument to measure small distances, to learn about big things far away, to me was a great attraction. That's what attracted me to the place.
Andrew, do you have something to please? Yeah.
Yeah, I didn't get the impression astronomers and particle physicists were fighting. The resources come from different places, so I don't think they were ever competing for funds. LIGO itself, what they've seen so far is something on a very big scale. The black holes were many kilometers across, and it's different from what particle physics are looking at as short scales. But in the long term, as they look, LISA or things which may look for gravity waves from the early universe, the general subject of gravity waves, and gravity in general is coming closer to. So it's a step in that, I would say it's a step in that direction. Yeah, it's a step in that direction.
So I'm sorry, time is out. Please, Monsieur, come to the stage and ask directly your questions to the speakers. As you know, I'm leaving you with a quote. So I didn't go to the past today.
You went to the future.
No, I went just 2 years ago. I had the great chance to do an interview with Kip Thorne for 2 hours. It was really fascinating. And he left me this nice sentence I leave you with. He said, cosmology will be the legacy of our time, just as the arts are the heritage from the Renaissance. It's nice. So do you have a reaction on that? That's the last words of the evening.
Yes, I have to say that, like I was saying, that we think of gravitational wave astronomy starting a new field like Galileo started astronomy 400 years ago. It's also a tradition that we will leave to the future. It's a new way of looking at the universe, looking at the dark side, the black hole, the one that doesn't emit light. Cosmology is a much, much broader area. I think that will live probably for the next millennium.
Thank you very much, Gabriela, and our two guests. Voilà, très brièvement, vous le savez, on arrive à la fin de cette semaine. Demain soir, Andrew Strominger sera sur scène. Merci à toutes les personnes qui ont préparé cette soirée, ce colloque en entier, et notamment, je le redis une fois, mais les traducteurs là-haut dans leur cabine qui font un immense travail. Et donc, il me reste aussi à vous mentionner le spectacle au Parc des Bastions, pour ceux qui n'auraient pas encore entendu ou vu qu'il y avait un spectacle au Parc des Bastions. Ça dure 20 minutes, c'est sur le thème de la gravité, c'est un son et lumière magnifique. Allez-y tous les soirs jusqu'au 21 novembre, à 6h, 7h ou 8h. Voilà, bonne soirée et à demain pour ceux qui seront là.